Yeah, so for the first question, we have this, we're interested in the probability that this random variable t, capital T, its absolute value is less than t0. And this has a probability of 0.9. So we can rewrite this absolute value as that capital T is greater than or fall in between these two range. So negative t0 and positive t0. And since t distribution is symmetric, so we can also write the center mass as 1 minus the lower tail. So 2 multiplied by by the probability that t is less than the negative, so the left-hand side, the left tail. And if we do 1 minus 2 copies of that, we will basically, it's the same as the center mass. And we still want the 0.9. And then it gives us the probability of t, capital T less than the negative t0 for probability 0.005. And from here, we can consult the t table and then look for the quantile, the left-hand side that makes the probability 0.05. And then you can solve for t0 from there. Okay, and then for part B, we are.
Why is the degree of freedom 8 there? Like problem is asking for 7.
Oh, this is from another problem set. The professor changed the number, so.
Should be the degree of freedom, right?
Yes, it should be based on the question. This one, yeah. Some of the question, for example, this one is 6, but the professor changed it to 4. So make sure the idea is the same. So the basic procedure is the same. Make sure you write down the numbers from the homework. This is from a previous quarter, so he just changed the number. So yeah. And then for part B, so yeah, we have I think 4 copies of random normal variables, and there's a keywords for independent, and that is the assumption that we're going to use for this question. So first of all is to notice that any general normal random variable x can be rewritten as or as a function as z, where z is drawn from a standard normal distribution. So for example, in this case, x can be expressed as sigma multiplied by z plus mu. And then based on the question, we have mu equal to 0 and sigma square equal to 4. So that we are able to rewrite each of the xi as 0 plus square root of 4 multiplied by a standard normal random variable. So with that construction, we can now rewrite the quantity of interest. So this is from the question, and then we rewrite each of the xi in terms of mu plus sigma multiplied by z. So this is 4, square root of 4, and then same as below. And then we can see that the constant term can actually be canceled out from the numerator and denominator. And then we are left with z1 over square root of 3 copy of standard normal square. And from here, we can then multiply by square root of 3 on both sides. So we have square root of 3 multiplied by c, and also we divide it by 1 over square root of 3 in the denominator. And by this construction, we basically have the left-hand side converted to a chi-square distribution for the denominator. Chi-square is just standard normal square, and then if you have n copies, then you basically have a chi-square of degree of freedom n. Here we have 3 copies of z square, so we have a chi-square of degree of freedom 3. And we also have 1 more copies on the numerator. And by divided by its degree of freedom, for example, this one is chi-square 3, and then we divide it by another 3 based on our construction at the beginning. Then we further decompose this quantity of interest into a t distribution with degree of freedom 3. And then from there, you can consult the t table again to look for the quantile such that this probability equal to 975. And then you can solve for c. Yeah. Now again, the basic idea is the same. Some of the number may be different based on your question. So yeah. Any question or comments? And also, I think I should mention something, or since I'm recording. So yeah, I receive lots of email every Monday, telling me to upload the video. Actually, I'm not allowed to talk about the solution, but I think going over the solution may be better for you guys. But it would be better. Don't email me just for asking for upload the notes or ask me homework question. Otherwise, I think basically the homework will make it meaningless. So the best way to ask question would be during the office hour or during the discussion. So don't email me homework question, as I'm also going over all the solution here. Yeah. So yeah. So the best way is through office hour. Yeah. I got lots of email last Monday. Any question or comments? Okay, yeah. Then for question 2, so we are asked to calculate, or I believe the question is some random variable, and then the quantity of interest is that the sample variance is less than a constant b, and then we are trying to find the value b that for 0.975. So one of theorem B from chapter 613, or a property, is that n-1 multiplied by sample variance over the sigma square actually follow a chi-square distribution, n-1. So yeah, with this property in mind, then we can rewrite the quantity of interest like this. So we multiply by n-1 and divide it by sigma square. That's we apply this transformation on the left-hand side. And then we can also implement the same transformation on the right-hand side. So n-1 multiplied by b and over sigma square. I think in the question, we also have the answer for n and the sigma square. And from there, we can just plug in a number. And then we have 2 over 3b. And then on the left-hand side, just a chi-square with this degree of freedom 6. And from there, you can just look up for a chi-square table for the corresponding degree of freedom and the probability, and look for the quantile and solve for b. Yeah. And similar idea for part B. I think, yeah, here we are looking for upper bound. Here we are looking for the lower bound. Same transformation on both sides. Look for the chi-square table, solve for the quantile, and then solve for the particular constant here. Okay, then for question 3. So in this question, we have 5 independent, again, there's a keyword IID. So yeah, we have 5 copies of xi for I from 1 to 5. And then each of them follow a general normal distribution. And yeah, again, we can rewrite each of the x in terms of z, where z is a standard normal, so 0 and 1. And yeah, since we have mu equal to 0, each of the xi is just sigma multiplied by zi. And we take the square, so sigma square zi square. We do the transformation for each of the xi. And the sigma square cancel out from numerator and denominator. Then again, we reduce the quantity into a division of a 2 chi-square distribution. So 3 copy of standard normal square give us a chi-square 3, a degree of freedom 3, and the denominator is a chi-square degree of freedom 2, and less than a constant. And we further divided the numerator by 3 and divided by the numerator by 3 and denominator by 2. And same implementation on the right-hand side, so 2 over 3 multiplied by c. And by doing that, we further decompose the ratio into a F distribution with degree of freedom, the numerator and the denominator, so 3 and 2. And it's still less than 2 over 3 multiplied by c. Then from here, consult F table for the corresponding degree of freedom and the corresponding probability, and then solve for quantile, and then for c. Yeah.
Can you explain again how you know to reduce from, I guess, the second to third term where you go to from that to the next one, and then also how you know to use F distribution at the end?
Mm-hmm. Yeah. So from here to here is that basically here is just more of applying lots of properties here. So for chi-square of degree of freedom, say n, basically you can construct such a random variable by drawing standard normal z, where z is sampling from normal 0 and 1. And then if you take the square and then sum over multiple copies, so for example 3 copies, then you will have a chi-square of degree of freedom 3. That is what how to construct on the chi-square. So with the sigma square cancel out from the numerator and denominator, for the numerator we are left with 3 copies of z square. So when you sum them together, you will have a chi-square of degree of freedom 3. So n copies, you will have degree of freedom n. And similar for the denominator, we have 2 copies, and then we have the chi-square of degree of freedom 2. So that's from here to here. And then from chi-square to F distribution, this is also like a property or characteristic. So when working on the ratio of 2 chi-square, when you divide it by its own degree of freedom for both numerator and denominator, you will reduce such ratio into a F distribution. And then the corresponding degree of freedom will be the one from the numerator, and the other one is from the denominator. So chi-square of 3 divided by 3 and chi-square of 2 divided by 2. You will reduce ratio of 2 chi-square into one F distribution for degree of freedom 3 and 2. Yeah.
Thank you.
And then, yeah.
For the first equality, the one with the variances in the z squared, if the variances didn't cancel out, it wouldn't be a chi-square.
Yes.
Right?
Yeah.
It's only chi-squared because they end up canceling out.
Yes. So the idea here is to construct what we want. So.
And so that they end up canceling out.
In this case, it cancels out perfectly, but some case it does not. It just in this case sigma square cancel out, so we are able to construct. Otherwise, it is not able. We are not able to do that. Yeah. That's the answer. Yeah. I think, is there another question? Or? Okay, then for part B. So in this case, the numerator and denominator are not independent anymore because we have the same copy for numerator and denominator. So this is the quantity of interest from the question. We can see that we have x2 and x3 on the numerator, and then x2 and x3 on the denominator. So we cannot just simply apply the same implementation here. So our first step will be taking the inverse. So we have 3 copies on the numerator and 2 copies in the denominator. And then we change the sign. So less than becomes a greater than, and then 1 over c. And then from here, we can then decompose this part here. So we have x2 plus x3 over x2 plus x3. So that's a 1. And then x1 over x2 plus x3. And the right-hand side stays the same. So that's the only, you can say, a small trick that we are applying here. And then move the 1 or minus 1 from both sides. We have this greater than 1 over c minus 1. So, and then from here, we can apply the same procedure as what we did in part A, constructing the chi-square or F for the solution. So then from here, now the numerator and denominator are independent. They don't share a same copy as before. And then we rewrite each of the terms in terms of z square. cancel out the sigma square, and then we have the ratio of 2 chi square. Again, divided by its corresponding degree of freedom, we reduce to f. So starting from a general normal to a standard normal, and then further to the ratio of 2 chi square, and then further to the 1 copy of f distribution. From here, look for the f table for the corresponding degree of freedom and the probability, solve for the quantile. Okay, part 4. Question 4. So I think this question is asking for method of moment to find the estimate for PDF. So we have PDF. The support is ranging from 0 to 1. We also have a restriction on the parameter space that is greater than -1 in the question. So first of all, we find the closed form solution, or the theoretical expectation in closed form. We can just use the definition for e of x, x multiplied by f of x, and integral from 0 to 1. 1 plus theta is a constant, and then x raised to the power of 1 plus theta. Evaluate the integral, we have this, and then evaluate it from 0 to 1, resulting in the expectation for this particular distribution, 1 plus theta over 2 plus theta. So this is a closed form solution for the expectation. And now we are also given 3 data points. And from the 3 data points, we can also calculate the sample average, where I use mu hat or x bar for that. So just 1 over 3, and then for the 3 data point. And for the method of moment, basically it is just asking, or we can just let the theoretical expectation equal to our sample average. So we basically just let these 2 quantities equal, and then solve for the only unknown quantity, which is theta in this example. And then we can we can see that theta hat is equal to 1 over 3, negative 1 over 3. It also satisfies the parameters, the parameter constraint that is greater than -1. And from there we can estimate the parameter. Any question or comments? Okay, then for question 5. So different from question 4, this time we have a discrete probability distribution. We have the corresponding sample space. So we have x can equal to 0, or equal to 1, or equal to 2. So we have 3 elements in the sample space. And we also have the corresponding PMF. So when x equal to 0, we have that p of x equal to 2 over 3 theta. And then when x equal to 1, we have this probability 1 theta over 3, and then 1 minus theta for 2. And then we take we apply the definition for the expectation for this discrete case. Basically just sum over all elements in the sample space multiplied by its corresponding probability. We have this in the closed form, or in this expectation can be expressed by the parameter of the PDF or PMF. So this is the theoretical expectation. And we also given the data point, 5 data point in this case. We take the sample average, and we have 6 over 5. Using the method of moment, we just let these 2 quantities equal, solve for the only unknown. And I think the parameters constraint is also between 0 or 1. So I think this one satisfies the constraint. So it is a valid estimator for our unknown parameter. Yeah. So 4 and 5, it's just using the method moment. We first construct the theoretical expectation in closed form, and then we find the sample average from the observed data, let them equal, and then we solve for the parameter of the distribution. Yeah, I think there's another part B for this one, updated by the professor. So make sure you also. So I think this is referring to part A, and then the professor also added a part B. So, but the basic idea is the same, and just don't forget about there's one more question in question 5. Any question or comments? Okay, then for question 6. So I think this one, similar to one electronic device, there are 2 components. Each of them is known to follow a gamma distribution with alpha and lambda. And we are asked for using the method of moment to find the parameter for the corresponding alpha and lambda. One thing to note or the question is, the observed data is regarding the lifetime of the entire device, which is the sum of the 2 random variables. So, but the alpha and the lambda is referring to the parameter of the individual components. So we are going to sum over the 2 components, and then using the method moment to bridge against the empirical observation. Yeah, so each of the U and V, which I denote for the individual components within a device, each of them follow a gamma distribution with alpha and lambda. And the sum of them, as what we did last time, is that I'll use X for that for one device, which is the sum of the 2 components. The sum of them, as what we've shown before for homework 1, is that it follows a gamma with 2 alpha and lambda. So this is the corresponding distribution that will be matched to our empirical or the observed data, which is the sum of the 2 components. And we now are going to work with the new or this new constructed distribution here. So regarding to a gamma distribution of 2 alpha and lambda, we have the expectation. So for X is equal to 2 alpha over lambda. And then the variance of X is equal to 2 alpha over lambda squared. And the variance is also equal to the expectation of X squared, the second moment, minus the square of the first moment. Yeah.
Wait, I think the expected value and variance of the gamma distribution is like alpha times beta. So why is it overlaying that line when there's no beta?
You mean why is the expectation like this?
Yeah, I thought the expected value of the gamma distribution was just alpha times beta.
Oh yeah, that beta is equal to 1 over lambda in this case. Yeah, there are, I think back in days, many researchers are doing, they're doing their own research. So some people call gamma distribution using alpha and lambda. Some researchers using alpha and beta. But the way, when they formulated the beta as 1 over lambda in this group of researchers. So yeah, so if you use beta or alpha multiplied by beta, then you can just make it, as long as you are your work is consistent with alpha and beta, then you should be fine. But in this group of researchers, or in my notation, I use alpha over 1 over lambda. Yeah, it's just back in days they use different notation. Yeah. But what they basically mean the same thing, or they formulate the same equation or PDF, but just they use different notation, which is just 1 over the other one. Yeah, so here I use alpha and lambda. And then the expectation is just 2 alpha over lambda, and then the variance is 2 alpha over lambda squared. Yeah, then we are going to bridge the moments with our sample average and the sample variance. So starting from here, 2 alpha over lambda, This is our left-hand side. And then for the right-hand side, we have 20 observed data. So we just take the sample average. I use X bar for instead of this summation term here. So we have one equation here that we are going to solve later. We also have the other quantity for the variance, 2 alpha over lambda square. So the right-hand side is the theoretical second moment, or the theoretical variance. And then on the right-hand side, we are going to use the sample variance. And or expectation of x squared minus the expectation square. And this 2 alpha over lambda square can also be decomposed into 1 over lambda multiplied by 2 alpha over lambda. And this 2 alpha over lambda is actually just the first moment, which we already know is x bar. So basically 1 over lambda multiplied by x bar is equal to the sample variance, so sigma square hat. So what we're doing here is just matching all the simulus term together, and then we list the equation for now, and then we solve for the individual unknown components. So now we have 2 equations and solve for 2 unknown, which is alpha and lambda. And so I think in this line here, we are solve for the lambda. And basically you can just rearranging the term. For example here, 1 over lambda x bar is equal to that, so lambda is equal to x bar over sigma square hat. Similar idea for the, 2 equation, 2 unknown, and then we have lambda hat, and now we solve for the alpha hat. And then alpha hat we can get from, we can also get from here, because we already know lambda. So basically you can just plug in this x bar and sigma square hat into this lambda. And we have this equation, we have the only unknown is alpha, and then you can solve for alpha hat equal to 1/2 over x bar square and sigma hat square. And now, and then this should conclude question 6 by expressing the unknown parameter from the observed data. So as you can see that the lambda and the alpha of the parameter of the PDF can be estimated if you observe the data. So so if you observe 20 xi, you should be able to calculate everything here for the right hand side, and then you can then further estimate the parameter of the distribution. And this is using the method of moments. I think in the future there will be some other ways to estimate the parameter. Any question or comments? Okay, question 7, or a follow-up question for question 6. So it basically given, we are given the same 20 observed data. And instead of estimating the parameters, the question is asking, based on the 20 observed data for the lifetime of each device, are we able to calculate or to estimate the differences of the 2 expected value? So the question is asking for the difference of mu1 and mu2. So question 6, what we did is that based on the data, we can estimate the parameter. And question 7 is that based on the same data, are we also able to estimate the differences of the two expected value? Yeah. So. And also we actually the question is also simplified by reducing the shape parameter alpha becomes a 1. So then this u, which follow a gamma distribution, it then becomes an exponential distribution. And I use lambda 1 for u and then lambda 2 for v. So our question or our the two distribution reduced to two exponential distribution. And then the quantity of interest is mu1 minus mu2. And we first rewrite this mu1 minus mu2 by taking the square. And then we have mu1 plus. Yeah.
Why do we take the square instead of just doing mu1 minus mu2?
I want to, in this slice, why I want to take square is that I want to construct the term into this, and later I will solve for lambda 1 plus lambda 2 and lambda 1 multiplied by lambda 2, two components. So basically the idea is to ease my computation by taking the square. But if you're able to directly calculating this the value for mu1 minus mu2, you can also do so. I think maybe I go maybe mine is more is not the simplest way. Yeah. But when I was looking at this question, I was just taking the square, and then I can construct the component there. And then later on, I find out that I can solve for the corresponding lambda 1 plus lambda 2 and lambda 1 multiplied by lambda 2. That's why I take the square. But maybe there's some easier way. But at least this is what I was when I was looking at this question. Yeah, so our quantity of interest is mu1 plus minus mu2. So first I just take the square and then resulting in this form. So mu1 plus mu2 square minus 4 copies of a mu1 plus mu1 mu2. So this is my construction, and then by plug in the parameter. So mu1 for the exponential distribution is 1 over lambda 1. Mu2, the expected value for the exponential distribution is 1 over lambda 2. And then I just plug in the corresponding terms, or in terms of lambda 1 and lambda 2, to rewrite this mu1 minus mu2 square. And then it result in this form. So once we have, we rewrite our quantity of interest from the question into this form here, and now we can just, or in my, in this example here, and then I'll just solve for the x1 plus lambda 1 plus lambda 2, and then lambda 1 multiplied by lambda 2. And once I have those quantity, I can just directly plug into this, and then it will give me mu1 minus mu2. So that is the reason why I want to take the square here, to ease my computation, or to solve for the components here, or more explicitly, the numerator and denominator here. So later you will see I can solve for the term without individual component. I can just solve for lambda 1 plus lambda 2 and lambda 1 multiplied by lambda 2. And I plug in this one, it will get me this mu1 minus mu2. And taking the square root, that will be the quantity of interest. Does it make sense, or if it's okay? Yeah. So So now I just write down the equation for here, and then I will then solve for the two component, or the numerator and denominator. So again, x is equal to u plus v, because our observed data is still the lifetime of the two components, so it still have to be u plus v. And then for the exponential distribution, the moment generating function is lambda 1 over lambda 1 minus t, and lambda 2 over lambda 2 minus t, as what we did in homework 1. And then the moment generating function for x is just the product of the two components. So lambda, and then we just multiply these two together. And this is the moment generating function for x, which is the u plus v. And then we are going to solve for the first and second moments by taking the derivative. So first order derivative resulting in this, and then the second moment resulting, or the second order derivative, even longer terms. Yeah. And then from here, we just let x or t equal to 0. We are able to calculate the first and the second moments. And then the first moment for the random variable x, it just resulting in this. And then the second moment it just resulting in this, which you can already tell that it looks very similar to our quantity of interest by the construction by taking the square. So this and this is what we are looking for, and then we can plug in number to solve for that. But from the moment generating function, we can also see some similar patterns here, and then later on it will ease our computation, and then in order to solve for mu1 minus mu2. So from the moment generating function, we get this and this one here, and also further calculating the variance. It's just the second moment minus the square of the first moment. Yeah. So now we have the left-hand side for the theoretical moments, first and the second order moments, and now we are going to bridge or to connect them with the this empirical average and variance. So this is the first or the expectation. We let it equal to x bar, which is the average of the 20 observed data point. And for the variance of x, which we get from here, we let it equal to the sample average or sample variance. And we also know this part already is, this part is it's just x bar. So the variance is just x bar minus this equal to the sigma square hat. And then we also find that lambda 1 multiplied by lambda 2 is equal to 2 over x bar square minus sigma square hat. So we have this part expressed in terms only with the data, and also lambda 1 multiplied by lambda 2 expressed or as a function only as of data. So now we have the two components that we are looking for. Then we plug in this x bar and then this part here back into the construction for mu1 minus mu2 square. Basically just this and this part here. And then mu1 minus mu2, which is this part. This is what we calculate at the beginning, and we can just plug in the two, the quantity. And then mu1 minus mu2 is just 2 sigma square hat minus x bar square. And then taking the square root, or expressed more explicitly in terms of all the data. And then this is just the estimation for the differences. And it has to be absolute value because we don't know whether under the square root is positive or negative. So whether the components, the quality of the components 1 is better than component 2 or the other way around. We can only we can only know up to the absolute value. But in the end, it's just the mean difference can be expressed as a function of data only. Yeah. So that answered the question based on the same data. Are we still able to estimate the differences? And the answer is yes, and then here is the estimation based on the data. Any question or comments? Okay, and then for the rest of the question, basically just plug in formula, plug in numbers, and then calculate. There's nothing much to explain for this part. So given that they are equal variance, so the 95% confidence interval for the difference, it's just the difference in the sample average plus and minus the the t-score multiplied by the variance of the difference, where the standard error of the difference, which is this pool variance multiplied by some correction term, and then the pool variance is this. Yeah, so basically just applying the formula, and you can find all the formulas from the lecture slides. So this is the confidence interval for mu1 minus mu2. Part B is looking for the sigma square, and this is the corresponding interval formula for that. So make sure you plug in the corresponding, and here I'm using the 4 data point from sample 1. You can also estimate using sample 2. And then for part C, just the confidence interval for mu1 with unknown variance sigma square. And then the formula is just x1 x bar plus and minus the t score multiplied by the standard error. So yeah, based on the question, look for the corresponding equation and then just plug in the number and make sure you plug in the right number for all the details, the sample variance or degree of freedom or the sample size. Similar for question 9. There's some technical explanation for the terms. Once you recognize calculate the corresponding differences, and then plus and minus the t score multiplied by the standard error. Yeah, so the d placebo here is regarding to the differences of the 5 after minus the 5 before, and then you have 5 differences, and then you take the average. That will be your d bar here. Then for part B, we have based on the definition on the hints, we have so before and after. So 5 after for the treatment minus 5 before for the treatment, and then we have another 5 for the placebo, and then another 5 for the placebo before. So we take the differences. So we have 5 difference for placebo and 5 difference for treatment, and then we take one more different. We take the average for the 5 difference for the 5 numbers, and then we take we do the minus or take the difference here, and then plus and minus the t for the standard error, and this is the pool or just the same formula here from as question 8. Okay, so yeah. Also, here I provided 2 solutions because the question did not specify equal variance or unequal variance. Yeah, so if the question did not, this question does not specify, so I provided 2. So one is assuming equal variance and unequal variance. So make sure you look for the correct formula based on the question. So yeah. Since the question did not specify, you should also provide the 2 as a practice. And then for question 10, the first claim is true. That's the definition for the confidence interval. The second one is incorrect because the interpretation should be that we are 90% confident that the true parameter is within this range. The C is also false because the claim or the interpretation is wrong. And then for the last one, 95% confidence interval. Previously, we have 0.28 as the confidence interval or the range, and the question is asking what would be the sample size if we want to shorten that to 0.1. So this is the construction for the confidence interval. We take the right-hand side or the left or the upper bound minus the lower bound, resulting in this, and then equal to 0.1. We already know that the previous one, which has n equal to 100, is 0.28. We take the ratio, resulting in the ratio of the 2 sample sizes is equal to the ratio of the two range, and then we can then solve for n, which is the sample size that we need if we want to shorten to 0.01 from 0.28. And that should conclude our homework 2. So yeah, So yeah, if you have any question, feel free to attend or to go to the office hour, or just not like email me before the due date for homework. I got lots of email, and it's just last moment, and then people are asking questions. Yeah, since yeah. Thank you very much.